Hello everyone and welcome to all of you in this big data series. So today we are going to discuss some of the important concepts used in big data with respect to database management. And these concepts are ACID properties, base properties and cap theorem. ACID properties are majorly related with SQL, while base and cap concept are related with the NoSQLs. So let's start these. Let's start to understand these three topics in detail. So first thing that we need to discuss before going forward is to understand what we mean by the transaction, because it is necessary to know what we mean by the transaction in order to understand all four ACID properties. So a transaction is nothing but a set of operations needs to be performed in order to execute a single logical unit of work. For example, transferring amount from account A to account B. So this operation can be treated as a transaction. For example, another example can be debiting or withdrawing, performing a withdrawal from some account A. This can be another transaction. So the meaning here is that if you are performing a transaction, there can be a sequence of operation in order to execute that unit of work. So in the whole discussion of ACID properties, we are going to consider same transaction example, and for that we have mentioned over here example like transferring amount 10,000 rupees from account A to account B. So when we are abstracting this thing at upper level, we are not going in the detail how database is doing behind the scene, what things they are doing. We need to understand this at upper level. So majorly, if we see this in that way, we find that there are two operation basically going on over there. One is, first operation is debiting amount 10,000 rupees from account A, and second operation is crediting of amount 10,000 to account B. So a transaction is said to be a successful transaction if it follows all four properties, and these four properties are termed as ACID properties. Now let's understand what we mean by the ACID over here. So in ACID, A refers for atomicity, C for consistency, I for isolation, and D for durability. Now moving towards the first property, atomicity. So atomicity states that if you are executing a transaction, it must be executed successfully or not at all. Means it should not be executed in the way that it performs some of the changes during the execution but not committed fully. So like in the previous example, if we are executing a transaction for transferring amount 10,000 from account A to account B, so after successful transaction, account B must have credited 10,000 rupees over there. It should not be the case that from account A 10,000 are got deducted but not credited to account B. If that the case occurs, we say that atomicity is not satisfied in our transaction system or our management system. So transaction ensures that if a transaction is going to be executed, it must be executed completely, or their effect should not be done in partial. Next property is consistency. It says that if your system is in consistent state, is in a correct state before the execution of a transaction, and if you say that that transaction executed successfully, then after the execution of the transaction, your system state must be in consistent state. To better understand this, assume that, let's suppose there are in a bank there are only two accounts, account A and account B, and right now account A has 50,000 rupees and account B has 70,000 rupees. Now we are performing the same previous transaction, means we are going to debit 10,000 from account A and to credit this to account B. So if initially we say that overall balance in the bank will be 50,000 plus 70,000 means 1,20,000. So when you are going to make this transaction, then you will see that from account A 10,000 will be deducted, and from B and to account B this will be credited. So if overall we will see the effect of the bank balance, it will be again 1,20,000. The meaning here is, in case if your transaction got failed in between the execution, means let's suppose we are going to execute the transaction and 10,000 is debited from account A, that means at that moment of time account A will have 40,000 while account B will have 70,000. So when let's suppose at that moment it got failed, means 10,000 is being deducted from account A but not credited to account B. So our overall system state will now become 1,10,000. In that case, we know that our data is not correct, because if we are performing the transaction within a bank and from only account A to account B, the overall system state must be 1,20,000, which is now 1,10,000. In that case, we say that our system is not in consistent state, or we can say that system is in consistent state. So our transaction must satisfy this property as well. Now next property is isolation. It says that if multiple transactions are being executed in parallel, they should not affect execution of each other. The meaning here is that in case we can say the assumption here is that we assume that at a time only one transaction is being executed. Now the problem will be if let's suppose there are two data items, account A and account B. If you are performing the withdrawal from account A and account B as well, one person is withdrawing from account A, another person is withdrawing from account B, then there will be no problem. But let's suppose both person are operating on same account A at same time, and let's suppose account have only 10,000 rupees over there, and first person performs a withdrawal of 10,000 from there. Similarly, second person is also wants to perform withdrawal of 5,000 from there. So if we allow both to work on that data item simultaneously, then definitely we are going to get some misinformation or wrong information over there, because if a transaction of T1 executed first, then account balance become 0, while if at the same time you allow for account B also, then it also get 5,000, and account and first person also get 10,000, which is not a valid scenario when you are going to perform over there, because ultimately our account is having only 10,000 rupees. So isolation ensures this, that if you are working on the same data item, then then those transactions must be executed sequentially, means one executed first, and after finishing of one transaction, second transaction will start. In that way we say that transactions are isolated to each other. And if you want to execute two transactions in parallel, then it must be considered over there that those transactions must not operate on the same data item. If data item are independent, you can execute transaction on parallel. Next property is durability. It says that if you executed a transaction and your transaction is successful, then the changes made by that transaction must be permanent. Means in case if any kind of failure occur in your system, it should not be lost. Means transaction effect must not be lost due to any failure if it got succeeded earlier. So in DBMS scenario, where we perform the transaction processing very well, we must, or our system must satisfy these properties, then only we can perform transaction processing over there. So for that we use the term OLTP, which refers as online transaction processing. Now moving forward to the base properties. Since when we discuss about the NoSQL databases, NoSQL databases are basically databases that are distributed to multiple servers, and due to this distribution, majorly they are made for the availability purpose, and that's why majorly when we are performing these when we are using the NoSQL databases, we try to avoid OLTP transaction over there, because these distributed system doesn't ensures the ACID properties properly, or we can say these properties are not hold every time consistently. Now what we mean by the base property? So in the base, BA basically refers for basic availability, S refers for soft state, and E refers for eventual consistency. So basic availability states that if you are working in a distributed system and if client is performing some task over there, your system must respond positively or negatively, but there should be a clear cut acknowledgement from the system. It should not be non-responsive, means a client sent a request and he is not getting anything from the system. So your system must be available all the time. If it is having the information, it must give that information in return, and in case if it is not having the information, it must acknowledge that this kind of problem occurred or this information is not there, and so that client can know that what the problem the system is facing right now. Second is soft state. It states that when you are performing the transaction, your system is going to change. Now assumption here is, since we are considering the system in a distributed manner, so might be when let's suppose considering a system is distributed in n locations, and for a particular data item X we are having two copies, one copy in one location and other two copies are at different location. And now if a client make changes in first copy of the data, then these copies must be updated on this information must be updated in another copies of the system. So the scenario is that it allows the changes, but the thing here is that these changes may not be performed at the same time to all replicas. So to ensure this, the next thing is comes is the eventual consistency. Like in case of acid properties, consistency says that if you executed a transaction, then the changes performed by the transaction must be consistent with the system state. Here the same thing is there, but the problem here is that we are having copies at different location. So the changes performed at one location may not be duplicated on the other replicas at the same time. Maybe they do these update later on. Maybe suppose one replica where suppose in the location where one replica is there might got down due to any kind of failure over there. So at that time that replica is not going to be updated, or due to the network complexity might be there is a delay in the communication as well. So we allow here is not a strict consistency but a eventual consistency. Means system must be in consistent state, but it may take some time in order to achieve consistency. So we can consider that this NoSQL system that works on the distributed environment gives the flexibility to the system that they can achieve these properties not at the same time, but they can achieve the consistency after a while. Now, to better understand this scenario, let's consider this payment example. Nowadays, major e-commerce site use this. So in this example, we are having two modules. One is the order service and one is the payment service, and these both modules have their own databases. Now let's assume that a customer places an order. So whenever a order service receive a place order request, it initiates a entry in its own record where it stores all the information of the place order along with the payment status as the payment initiated, and then it forward this all information to the payment service there so that they can make payment over there. So after receiving this request from the order service, payment module start serving to the payment over there. So client can perform payment over there. Now let's suppose we are assuming the case when this payment got failed at the user end in case of any reason, might be wrong CV or expiry date, any reason might be there. So in that case, what payment module does, it stores the information of this transaction where might they might have updated the status as payment failed, and the same information is sent back to the order service so that order service can also update this field with the payment failed and can give the alternative way to the user for making the payment. And these two states continuously runs until the payment got succeeded. And whenever payment got succeeded, first payment service module updated status to payment complete, then it sends this information to order service, and then order service update this information to payment service. Now here one thing is clear, that they are not strictly following the ACID properties over there, because in case of ACID properties it says that if payment failed, your whole transaction must be rolled back. But in this case we are performing the transaction on the module basis, but the overall status is following the base properties. Means after some time consistency can be over there. So the scenario here is when the payment made successful while the previously it got failed, so at that moment of time order service will receive will have the status that payment failed, while when payment service module got succeeded, it will have the payment uh, complete status. So at the that moment of time we got the two information. One information is having the failed status, and one is having the uh, complete status. So this kind of scenario might be there, but we all know that after certain time both the databases will have the same consistent state related to that order. Hope this is clear to all of you. And now the next property comes is our next basically concept comes is the cap theorem. So cap theorem is again majorly used for the distributed environment, and the cap states that the C refers for the consistency, A refers for the availability, and P refers for the partition tolerance. Consistency again in case of distributed environment, since we are assuming that if we are having some piece of information on one system, its replica must be available on the some other system, so that we can get access to those information positively, and our system becomes more available to the user. So consistency says that if you are having the multiple replicas of a record, every replica must contain same piece of information at every point of time. Next property, availability, says that if you are having the multiple active node or multiple base locations where your information is stored, these locations or these nodes must be available to respond to the client. And the third one is the partition tolerance. Means if you are partitioning your information to different node, the user must not be affected by this partition. If he or she wants some information from the system, whether it is located on multiple location together or not, user should not be affected by that, and they can get this information seamlessly. So when we are talking about this distributed environment, it is necessary that your system must follow partitioning over there, partition tolerance over there, along with one of the consistent or availability. The major part of the cap theorem is it states that whenever your system is having availability and fault tolerance and partition tolerance, then there is a more chances that they are not going to follow consistency strictly. Similarly, if your system is following fault partition tolerance and consistency, then your system is not going to follow availability completely. So here we can see an example of MongoDB. So MongoDB says that your system is capable of performing the partition tolerance perfectly, along with it also maintains the consistency of the system. So during this, it makes sure that it is not going to follow the availability criteria completely. Might be some of the information may be available, and sometime your information might not be available due to maintaining your consistency of the database. Similarly, another database is Cassandra. Cassandra focuses on the availability of the system along with partition tolerance, and it says that if your system might not be consistent might not be in consistent state, but your information will be available every time. And the next one is MySQL, which is different from other two. And since we know that MySQL is a kind of master slave architecture, that means here overall database are deposited at one location only. So partition tolerance is not over there, and it strictly follows two things: consistency and availability. To ensure the availability also, it can have some kind of replica mechanism over there. Now the next thing is why cap theorem is saying that you cannot have all three together. So to better understand this, we can consider the scenario that you are having your data partitioned to n location A, location B, location C, and up to n location, and every piece of information or every record is copied at three other locations as well. Means if a piece of information is available at location A, it must be available at three others location, let's suppose at B, at C, at D. So if your system is saying that you need to perform, you need to follow availability strictly, means your system should be available all the time. So the mean there is that in case if any of the system responded to you, you can give the information to the user. But the problem might be, let's suppose a user is performing the write operation in copy A, and that update is not propagated to another replicas present on some different nodes. So at that time your information will be available to all the nodes, but it would not be updated in all location. That means when you are assuring that your system should be available to the user, your copies of the data might be inconsistent for some time. Similarly, if you want to make sure that your system must be in consistent state, means in case you are performing a change to one location, then other replica of that item must be unavailable to the user until they got updated with the current copy of the data. So for that you might perform some kind of locking mechanism for there. So definitely if you are performing the locking mechanism, at that time that information is not available to the other users, so you need to compromise with the availability at that moment of time. So this is the aspect that cap theorem says that if you are going to work with the partition tolerant system or distributed system, you can only strictly follow either consistency or availability. So that's all from my side. In case if you have any question, you might post your question or query or doubt in the comment section, and please like, share and subscribe my video.